It's great to be here. Back at Goddard, I started my career here at Goddard, so many years ago. So it's kind of a blast from the past. I actually haven't been here very much since then, but it's fun. It's fun to be here and nice to see you all. So yeah, as Frank said, I'm in the Office of Public Outreach at Space Telescope and kind of responsible for putting these images together from the science data. So that's kind of what I'm going to be talking about. Frank gave a great introduction to this because he talked about the theory, kind of the ideas behind filters and light a little bit and how we use them. So I'm going to do more of the practical application of that, talking about how we use that technology, those ideas, to produce the pictures from the Hubble Space Telescope. And I'm going to start out and just again show you, Frank already showed some of the images, kind of talking about the range of the kinds of things that Hubble does. Hubble's a very multi-purpose observatory. It's specialized in some ways, but it's very multi-purpose. It's a general purpose observatory. So we look at everything from the solar system. This is the planet Jupiter, of course, which with its great red spot, which is actually is red, as we can see in the image. We look farther out to stars. This is a cluster of stars, the very core of a cluster, a globular cluster. These gigantic conglomerations of hundreds of thousands to maybe even 1 million stars in this spherical conglomeration. Hubble's great resolution and contrast enables us to separate these stars individually. We can study these stars individually, whereas from the ground, because of the obscuration of the atmosphere, the star images are blurred together and we can't separate them as easily as we can with Hubble. So that was one of the fundamental things that Hubble was designed to do. We go farther out. This is an area where the stars are being formed out of these great clouds of gas and dust. The dust compresses into these condensations and stars are being formed. And there's actually telltale signs of that. Here we see jets of material coming out from these columns of material, and we know there's new stars formed down there. And again, give you an idea of what's going on in here. The different colors show different things. I'll talk about that in more detail, but just to give you an idea of the range of things we're looking at. I should have pointed out in the previous picture, in the star image, you notice that these stars have very strong colors, a lot like the LEDs we were looking at. And again, using the filters, this is kind of a preview, using the filters we actually distinguish those stars very greatly and can measure very accurately the colors of those stars. But that's so it's actually kind of an unusual star image in that the colors are so strong. When we look through a telescope, look at stars through the telescope, we don't see strong colors like this. And that's another thing I want to talk about in doing these color images, why that is. And we'll talk a little, well, I should mention now that the stars have different colors because they're different temperatures. The stars are different sizes, they're different masses, they're different temperatures. And the temperature entirely defines their color. So a cooler star will appear red because it's producing more red light than blue light. Hotter stars appear bluer because they're producing more blue light than red light. That seems a little counterintuitive. We sort of think of red being a warm color, and blue being a cool color. But in physics, it's the other way around. Cool stars are red and hot stars are blue. So going back to so this is our star formation region. This is a star death region. I believe you already saw this picture, although this is kind of a detail of it. This is a star, a supernova star that blew itself completely apart, or almost completely apart. There's a remnant star down in the center that's energizing this material that it blew out from itself and causing it to glow. And again, we see different colors. And those different colors come from the different materials, the different elements that are in that gas. Again, going farther at this, all this stuff that I've shown before is in our own galaxy. So we live in this galaxy, this giant conglomeration of stars and gas and dust and rocks and stuff like that. The galaxy we live in looks something like this. This is another galaxy we're looking at much, much farther away. We can't see our galaxy because we're living inside of it, but we can see other galaxies, and we've kind of figured out over the years that our galaxy is pretty much like these other spiral galaxies. There's all kinds of different kinds of galaxies. This is one of the dominant types of spiral galaxy. A subtype of that is a barred spiral galaxy. It has a straight feature in the middle, the ends of which the big spiral arms are coming out of that bar. And again, the colors are real. The colors come from different things we're looking at in this galaxy. Again, the blue, we know the blue stars are hot, generally massive. So the blue spiral arms trace out areas where new stars have formed, and preferentially when the new stars are formed, you see more big hot ones. Older populations, like in the center of this galaxy, are predominantly cooler stars, smaller stars. The big hot ones end their lives, use up their fuel much faster, and they end their lives sooner. So they don't live as long, don't last as long. The older stars, the cooler stars, tend to live longer, and so we see more of them towards the center of the galaxy. Then there's also these kind of filaments, these red filaments. Those are dust lanes, which again indicate these areas where new stars are being formed. They are red because they're absorbing blue light and letting red light through. So the colors are relevant. The colors mean something. The colors are there not because we've put them there, but because they fall out of the data. Going out much farther in the universe, this actually ends up being one of the most significant images that Hubble's made. It's called the ultra deep field or extreme deep field, depending on who you talk to. It's a patch of sky that Hubble looked at repeatedly over many years, actually. Cumulatively, it's several weeks worth of data continuously, but it's not observed continuously. It's been observed in stretches spanning many years, actually a decade or so. And we're seeing very, very far into the universe. So we're seeing among the farthest things that we can see, we can detect. We don't see them with our eyes, but we're detecting them. Almost everything you see here is a galaxy. It's a galaxy that's roughly the size of our galaxy. So they're small because they appear small because they're so very, very far away. There are a couple stars here. The diffraction spikes show that there's a star that's in our galaxy. So when I look at this, I almost get a sense of vertigo because I feel like I'm looking into this abyss, almost like looking down a very, very deep canyon. And because we're looking through the entire range of the universe. It's not that we're looking just at the farthest stuff. We're looking at everything between us and the farthest stuff. So to me, it's kind of an amazing kind of image. And again, the colors are real because the different galaxies have predominantly different colors for several different reasons. This is not a talk about galaxies, so I guess I won't get into that. To get a little bit more into the kind of mechanics of the images, you may be familiar with this image. It's probably one of the most reproduced images from Hubble ever. Astronomers call it M16, Messier 16, or the Eagle Nebula. It's a tiny little detail of this giant star-forming region. Amazing image. I can talk. This was taken back in 1995 with the fairly newly installed wide field planetary camera 2, WIFPIC 2, which was the camera that fixed the problem with Hubble's main mirror. So when it was launched, they figured out that the main mirror had a flaw in it, meaning they could not get sharp images from Hubble, which was really kind of ironic because it was built to make the sharpest images ever from in space. So unfortunately had this problem, but it was the kind of the best problem they could have had, because it turns out they could characterize that flaw extremely precisely, and they could create optics that would compensate for that flaw, and relatively easily. I mean, it's very difficult to make very precise optics, but as this stuff goes, it was relatively easy. And in fact, when they designed this camera, it turns out that all they had to do was build this one little mirror about the size of a nickel, but it had to be ground and polished just the right surface to counteract the flaw in the primary mirror. And that's really all it took to get the images that were then perfect. So anyway, this year is the 25th anniversary of the Hubble Space Telescope, so we thought it'd be a good idea to revisit this since we have new instrumentation on the telescope. Since we've been able to service it, we've been able to keep up with technology a little bit and install new instruments that have better capabilities. So that's in fact what we did. So we were able to produce a new image of the same object with the new camera called Wide Field Camera 3, which replaced the Wide Field Planetary Camera 2. And it's a better detector. We've learned a thing or two about building cameras in 20 years or so. And we were able to get a wider field, so we see much more of the surroundings and much more of these columns of material. And it's higher resolution. You can't really tell that in comparing these images in this way, but if we zoom in a little bit, we can see a lot of really interesting details in this image. Now the other thing that this camera, this was taken in light that we can see, in visible light. Sometimes astronomers call it optical because we can see it. But this camera, the Wide Field Camera 3 is actually two separate cameras. One takes images in visible light, mostly. The other one takes images in infrared light. And that ends up, and we took an image with the infrared camera also, the same region, and that's what we see, or mostly what we don't see. The columns have pretty much disappeared, but we do see a lot more stars. And so again, this is the nature of light, the nature of absorption of light, as we were seeing with the filters, and the emission of light. So there's all kinds of light being emitted here. There's visible light, there's infrared light, there's ultraviolet light. What we're seeing in the previous image is all visible light, light that our eyes are sensitive to. This image was taken in infrared light that our eyes are not sensitive to. It's redder, longer wavelength than the reddest light that we can see, but you can build a camera to detect that kind of light, just like you can build a camera to detect visible light, and ultraviolet light and all kinds of different light, X-ray light even. So why are we seeing so many more stars? Well, those stars didn't suddenly appear. Those stars were there and shining in all kinds of different light. The reason we can see them is that the dust and other material in this area is blocking the infrared light preferentially. So in the visible light image, just like with the filters, you'll see the blue LEDs through the red filter, you don't see much of anything. The same thing is going on here. With the infrared, with the visible light filters, you're not seeing any of that infrared light. With the infrared light filters, that infrared light is coming through the filter and the visible light is being blocked. So that's why we don't see the columns as much, because the columns are emitting mostly invisible light. Now if we go farther into the infrared, like the follow-on to mission to Hubble, which is actually being built right here at Goddard, the James Webb Space Telescope will be entirely operating in the infrared. In fact, it'll be sensitive to wavelengths in infrared much farther than Hubble's infrared camera can. So in fact, if you go farther into the infrared, then these columns of dust start to glow themselves. So we'll see these light up. If we take an image of this with the James Webb Space Telescope, which I really hope we do, we'll probably see these things actually start to light up again. So that's kind of an introduction to the kind of stuff we can see in general. How do we do that? Well, we do that with this camera on the telescope. This is the Wide Field Camera 3, the new camera that was installed, well, not so new anymore. It was installed in 2009, 6 years ago. And on the right, you see the actual detector. So that's the piece of electronics that actually gets the light, the image from the telescope. The telescope mirror collects the light, collects a whole bunch of light, because it's a giant mirror, and focuses it onto this piece of electronics. And that piece of electronics translates that light into numbers. And the brighter the light, the bigger the number that it records. So it's got about 4 million sites on there, pixels on there. And people are sort of familiar with pixels and pixel counts and cameras, and they kind of have the idea that more pixels is better, and in general it is. In some cases it's kind of diminishing returns, having more pixels, but in fact this camera has roughly, sorry, I think I misspoke, 16 million pixels. It's about 4,000 by 4,000 pixels. So it has about 16 million pixels, which is a pretty decent camera, and even by today's standards. So we make 16 million measurements of the brightness of light in one exposure. And that's all we're doing, really. Fundamentally, we're measuring the brightness of light over this little area, the little patch of sky. With the telescope, we're able to collect a lot of light, and we're able to, and because it's a detector, it's not our eyes. Our eyes are instantaneous detectors. We can only detect light that over roughly about 1/30th of a second, the light that accumulates on our retina, we see as an image, as light. Film, if you remember film cameras or electronic detectors, you can accumulate an image over time. Essentially the longer you expose, the more light you can detect, the fainter light you can detect. So that's what we're doing here. We're trying to collect as much light as possible with a bigger telescope. The bigger the telescope, the more light it can collect. And we've got detectors that can build up an image over time. So the longer you expose, the more light you can detect. But it's still a black and white detector. It's a monochrome detector. It's nothing about color yet. On the cameras that you have, regular consumer cameras, whether it's a cell phone or a standalone point and shoot or a high-end digital camera, they are able to record color pictures because the technology is a little bit different. All color technology works essentially the same. As we've seen with these filters, you can break up the white light that we see. White light is composed of all the colors, and which is demonstrated nicely by a rainbow, where sunlight passes through some water droplets and breaks that light apart into its constituent colors. So here we have a rainbow, the kind of light that we can see and beyond. So I think of this as kind of a hyper rainbow, going from the ultraviolet at the left side to infrared on the right side. Shorter wavelengths on the left, longer wavelengths on the right. Longer wavelengths are redder, shorter wavelengths are bluer. So this represents the filters inside the Wide Field Camera 3. So there's actually a physical wheel inside the camera. On the edge of it, there's these holes, and in those holes, they have colored glass filters that are selecting which part of that hyper rainbow we're gonna see, we're gonna look at, we're gonna record. Now, there's two pieces to this. As I said, there's a visible light camera and an infrared camera. So on the right is the infrared portion, way out here in the light that we can't see of this hyper rainbow. But the infrared camera also has filters. It doesn't have as many as the visible light camera does, but it has filters. And that's what's represented here. So each filter is taking a chunk out of that white light spectrum and throwing away all the rest, by the way, which seems kind of weird because we spent a lot of money to build this giant telescope that gathers all this light, and then we're throwing most of it away with each exposure. But that's the way astronomy has to work. We haven't figured out any other way to do it. Going back to the astronomy part, so this is a representation of a spectrum of a star. The amount of light that's emitted by a star, by a representative star, at the different colors at different wavelengths. So this is kind of an average star. It's a little bit cooler than our sun, so it's a little bit redder than our sun. But as you can see, it emits light in this large range of wavelengths from the ultraviolet, and most of its light is coming in the blue, and then it tapers off, and it's still emitting all the way through the spectrum into the infrared, but it's much less red light than blue light. So these are the kinds of filters that we would use to sample that light and observe this star. And one of the things we can do is measure the color of that star. If we take an observation over here in the blue and take another observation over here in the red, it's pretty obvious that we'll get more blue light than red light, so we'll call this star blue, because it'll appear blue if we combine those. And we can do the same thing in the infrared as we do in the visible, but this particular star is not emitting much infrared, so it wouldn't probably do us much good to observe this star in the infrared. Now, there's another whole class of objects that we can look at, and we've seen some of those. These gaseous nebulae, like the Eagle Nebula, like the place where stars are being formed, these guys preferentially emit light in very narrow ranges of wavelengths. Instead of a star or a conglomeration of stars like a cluster or a galaxy, which emits light in this huge broad range of wavelengths, these nebulae emit light in these very precise, very narrow colors. They're very pure colors. So, and this comes from the fact that specific chemical elements are emitting these particular colors of light. And each chemical element has its characteristic wavelengths that it emits at. So hydrogen predominantly emits wavelength at this red light frequency. It emits light at other wavelengths too, but most of the light, under most of the conditions that happen in space, mostly red light. Oxygen, similarly, mostly emits in this cyan or blue-green light, and so on. Helium emits down here in the blue to violet, and so on. So that's kind of cool, because we can actually study these areas very carefully by measuring the brightness of this light in these very specific wavelengths. Well, how do we do that? Well, we can design a filter that matches that particular wavelength. Most of the filters we're familiar with, like the glasses we've been dealing with, are these broad filters that transmit a large range of wavelengths. However, we can design, it's much more difficult and much more expensive to design a filter that only transmits this very narrow range of wavelengths, but it's possible. So that's what we do. So in getting to the actual images, this is kind of the range of things we do. We have to process the data that comes off the telescope, which happens with whether we're making pictures from it, which is kind of the byproduct of the science. Most of what happens with the data is astronomers take that data and figure out stuff, what's going on, by studying that data. And whatever we do, we're essentially translating the numerical data that the camera recorded back into brightness values of some sort. And then what we do is produce the color images, which is not really part of the science necessarily, but it's generally for the public to, what we're doing is illustrating the major discoveries from Hubble. And that's kind of my job, that's the job of our office that I work in, to tell the public, you guys and everybody else, what's going on with Hubble, what Hubble is learning, what we're learning using Hubble and other telescopes. But we want to illustrate that, and fortunately we have these nice images to help do that. And then we'll treat it like any other digital photograph. We're able to improve that image. So what about this data processing? Well, to kind of exemplify that, there's a lot of processing that happens on the data, but we don't need to worry about it. Just as an example, one thing that happens is there's all these energetic particles floating around out in space called cosmic rays. Some of the origin of some of those is still a bit mysterious, but we know where a lot of them come from, but they're all over the place. Fortunately, most of them get absorbed by the atmosphere, and we don't need to worry about down here, but out in space, it's kind of a problem. It actually, when they hit the detector, they cause a bright spot on the detector, even though it has nothing to do with this object we're looking at, but we get these all over the place. So it looks like somebody shook a salt shaker down on the picture, and we get all these cosmic rays. Fortunately, they're random, so if you take two images of this exact same thing, just don't change anything on the telescope, take one picture, and then take another picture, you'll get a completely different set of cosmic ray hits. And by combining these, by taking the real stuff and throwing away the cosmic rays, we end up with a nice clean image. Now if you look very closely, you probably can't see that from back there, but there's some other things that are going on in this image. There's some defects in the detectors. They're not perfect. They're as good as we can make them, but they're not perfect because we're not gods. We're human beings. But these defects in the detector can also be removed by similar kinds of processing techniques. Just to give you an idea that there's a lot of stuff that happens to this data before either the scientists get it or we get it to make the pictures. So then how do we go about making these pictures? Well, the first thing you want to do is just look at the picture. So if you just look at a picture here, displayed on your computer screen, this is kind of something like what you might get. You see some bright things here, and you see some maybe fainter stuff down near the mostly black background. Well, you kind of expect the background to be black. Space is largely black, punctuated by lots of bright stuff, which is still faint because it's so far away from us. However, since this is data, digital data, we can process this in various ways. So the first thing we want to do is rescale this so that it's a lot brighter. And oh, lo and behold, we see a lot of cool stuff down here. This is a little group of galaxies. There's a lot of material between these galaxies that we're now starting to see. And there's a lot of material in these galaxies. But the problem is, now that we've cranked up the brightness, we've kind of lost some of the information, some of the detail deep within these galaxies, which we had in the previous image. Fortunately, again, because these are numbers, this is data, we can work with this data, we can represent it in a different way, we can have the best of both worlds. We can display this, visualize this in a way, what we're doing is transforming those numbers that the camera recorded into brightnesses on the screen. And we can do this in a more clever way such that we see all the faint stuff near the dark background. There's faint stuff all the way through here. In fact, there's background galaxies that are much, much farther away that we're seeing if we brighten it enough. But we're also seeing all the detail deep into these. In fact, this galaxy, it has a nucleus, but it's not as bright as this nucleus. So we see the whole range of brightnesses. Yeah?
So is this anything like HDR?
It is, in fact, a lot like HDR. HDR refers to high dynamic range, which is a technique in photography where you can extend the range of brightnesses which you can represent on a screen or on a print. Where on a bright sunny day, not like today, but a bright sunny day, you'll have in just a landscape, you'll have very bright areas which are in direct sunlight, and you might have shadows, deep shadows in, say, a forest, and the brightness difference between the bright sunlit side and the dark shadow side is immense, much more than you can represent in a display like this. So we use techniques like that to compress that dynamic range, and that's exactly what we've done here. There's a technique in photography where you combine multiple exposures, taken at different exposures. You expose for the shadows, as a photographer would say, you expose for the highlights and combine those. This is a single exposure essentially, but the cameras itself have very high dynamic range, so you can pull out those details in a single exposure. So just to reiterate, we're producing images from data. We're not colorizing images like movie studios might introduce color into an old black and white movie. That's not what we're doing. It's not paint by number. We're not assigning a color by the brightness of each individual pixel, although you can do that, and that's an effective method of visualizing an image under certain circumstances, but it doesn't necessarily relate to what's going on in the actual object you're looking at. And we try to keep the processing, the manipulation to a minimum. We do use Photoshop and other software to work on these images, but we're not Photoshopping, if you, in the sense of falsifying something. So again, just to hammer this home, you had the filter demonstration. What we see when we look through colored filters at a essentially white light scene, we're seeing blue light, green light, or red light. These are in fact the three primary colors, or more technically the additive primaries, which when added together at different intensities produce all the colors that we can see with our eyes. And in fact, that's how our eyes work. Our eyes are separating the scene into these roughly these primary colors, and our brains are reinterpreting that into a color scene. So every color technology works like this. The cameras in your phone, your point and shoot camera, whatever. In fact, those detectors have little filters over each pixel, and it's either a red filter, a green filter, or a blue filter, and then the computer inside the camera converts that back into a color image, and that's exactly what we're doing. Well, the cameras on the telescope, as I said, do not work like that. Each pixel on the camera only records the intensity of light without any filtration. So we have filters introduced in the camera over the whole detector, so every pixel on the detector is seeing the same color of light. Whereas in your camera, each pixel is seeing a different color of light. Well, one of three colors, red, green, or blue. So again, Hubble's cameras, this is what Hubble's cameras see with those same filters, gray images. But we know what filter we use to take that picture, which is very important. So here's a real world example, kind of. Again, the same picture, this little cluster of galaxies taken in red light, yellow, greenish light, and blue light. So again, the pictures all look gray, black and white, but they were taken in different colors of light. So what we do simply is apply a color to that, red, green, and blue, the additive primary colors. We could use different colors. We could use, say, orange or cyan or yellow, but it turns out those are not the additive primary colors. Those are actually combinations of colors themselves, and we would not get as broad a palette of colors, and I think you'll see that in a later demonstration. So these are the three additive primary colors, and this is the color image you end up with. And it's just simply combining those images. It's magic to me. Every time I see it, it's magic, but it's not magic in the sense of we're not pulling the wool over your eyes. It's just what falls out of the data. So the red parts that we see are red because there's more red light there. The blue parts that we see are blue because there's more blue light there. And that's what's coming from space, captured by the telescope, recorded by the instruments. And then that's the final image. Now, there's another whole regime here, and I guess I went one too far. And again, going back to that first slide, spectrum slide, there are these narrow band filters. There's these places which are emitting light preferentially in very precise colors. These gaseous nebulae that are, because of the physical conditions, the material there is emitting in these particular colors. So we use particular colored filters to sample those particular colors very precisely. So here's an example. So these are the colors of the filters. They are really different. These two, whoops, again, went too far. These two look like the same color, but in fact, we're sampling with this filter, we're sampling the light of hydrogen. With this filter, we're sampling the light of sulfur. They're separated enough in wavelength that we can separate those out. And then we're also sampling oxygen light, which is emitting in cyan. So that's the colors that we would see looking through those filters. Of course, again, Hubble sees black and white images. However, if we reintroduce those colors and combine them, this is what we get. Now, that's not the image we saw before. This is rendering those images in the colors of the filters themselves. So that's what you get. Not very satisfying to my eye. If we play a little bit of a trick, though, I shouldn't use the word trick, it's just I'll say a technique, okay? Instead of applying the colors of the filters, we'll apply the standard additive primary colors, red, green, and blue, to those filters. Now, we've applied them in a clever way, in the sense that the bluest light, we're gonna make blue, make that image blue. The reddest light, which is coming from the sulfur atoms, will make red. The one in the middle, which is coming from hydrogen light, in wavelength terms, that's a little bit bluer than the red light coming from the sulfur filter. We'll make that one green. We'll make it green instead of red. But here we have the additive primary colors. So what do we end up with? We end up with the remote that doesn't work. Oh, we end up with the picture we saw before. So, and to my eye, this is much more satisfying because we have a broader range of colors. In the previous image, we essentially had a monochromatic or two-color image because we were starting with 2 colors. Here we're starting with 3 colors, 3 well-separated colors. So we're seeing a lot of separation of the colors. We're seeing blues and yellows and in fact greens and reds. So this is a technique to get the most out of the data. Yes, Frank?
I would also add that the color separation images with the RGB are more useful to astronomers as well, because then the astronomer can look at that and say, well, you see the blue in the background, that's the oxygen emission, and then you see the little red around some of the stars, that's going to be more in the sulfur emission, and you can actually scientifically pull out the colors better, whereas if you had colored both the sulfur and the hydrogen red, they'd be mixed together and you couldn't pull them apart.
Exactly. So we're getting more information, and that's kind of my philosophy about all this. My goal is to visualize, to represent as much in the images as possible that's inherent in the data. So that's the goal, both in terms of tonality and bringing out the different levels of brightness, but also in the colors as well. So the last bit, I'll just go through the more kind of, so I always think of this as a combination of art and science. So the science part is transforming those data values into brightnesses on the screen and so forth, and assigning the color and combining those images. The art side is more taking a raw image and turning it into, I won't go so far as to say a work of art, but a much more interesting image, and perhaps more powerful image, an image that really shows what's inherent in that data. And so through a number of steps indicated here, color and tonality and so forth, contrast, we can actually change this image and adjust it in a way that may be more pleasing. For example, well, I won't go back because I'm going to have to go back to the beginning, but for example, there's some odd color in the halos of these stars. That's a kind of an artifact of the filters themselves. It's not really inherent color in those stars because these are these narrowband filters. Again, if we were using those broadband filters, we would get better colors of the stars, but we're after the color of the nebula here and not the stars. And that's kind of the disadvantage of using these different kinds of filters. So everything has strengths and weaknesses, right? So we just go through a number of these incremental steps and end up hopefully with a more pleasing image. And another thing you might notice, there's some funny features here. They don't look like stars. They don't look like they're part of the nebula. Well, what those are, in fact, are reflections that happen within the camera. So there's all kinds of optical effects going on here because of the nature of light. So one thing we see is these spikes on the brighter stars. Those happen because light is being bent around structures in the telescope. There's a structure that holds a secondary mirror that bounces light back from the primary down into the instruments. Well, if you have enough light from these fairly bright stars, you will record the light that's being bent around these structures. We tend to leave those alone because they're kind of, people expect bright stars to have diffraction spikes. This stuff, however, is a reflection, and from these bright stars, you get reflections inside the camera. There's lots of optical elements inside the camera, there's windows and stuff, and again, if the light is bright enough, the amount of reflection is teeny tiny. So in general, it doesn't affect the what you're looking at. But if you have a very bright star and relative to the brightness of the other stuff in the image, you'll get effects. You'll actually record that tiny minute amount of reflection that you get inside the camera. So that's what's happened there. We'll take those out just because they're distracting and they're not part of the actual image. And then you kind of notice these edges are kind of weird. There's a couple of effects going on there. The camera actually introduces some distortion because, again, optical effects, so where it is in the telescope and stuff and how the optics are designed, it creates this distortion. So when that distortion is taken out, the image actually gets skewed a little bit, but it's like not a big deal. We'll crop that out, and then you see this funny stair-step edge. That's because we took multiple images and shifted the telescope a little bit. So we've combined all those images and we get these interesting effects. Again, just to make a cleaner image and a less distracting one, we'll crop it down a little bit, and that's our final result. So there you have it. So I think I'll end it there. I'm happy to answer any and all questions, and thank you for your attention. I guess not. Okay. Yep.
What a sensor like is in a cell phone camera that is picking up separate red, green, blue channels. Would a sensor like that be able to effectively do the same thing in the Hubble, for example? If you got a sensor like that, could you do what you do with filters with the sensor?
Well, we'd be severely limited because the filters would be fixed to those filters that are attached to the sensor. Now, in principle, you could have another filter that would limit what light the sensor sees, but you've severely limited yourself. For example, if those filters in fact are simply red, green, and blue, and they're absorbing everything else, you couldn't do any infrared, for example, because that would be outside of the range of the detector and filter combination. So even if the sensor itself, the pixels themselves were sensitive to infrared, you've blocked it with the filters on the sensors. So, and that's why we do it this way, because we don't want to limit it.
Well, I've heard about with like a home telescope with a camera on it. Could you use that channel data to sort of do the same sort of experiments, like see what's in the red and the green?
Oh, sure. You could separate that out in principle. Yeah. In fact, the raw images that you get, if you get the raw image out of your camera that's very close to, and you take the red channel and the green channel and the blue channel, you could separate those out. It wouldn't do you any good for processing the images necessarily, but yeah, you could see what's there in the red and the green and the blue, yeah. Yep.
I used to have my students look at my infrared remote through their camera phones, and now, last year I tried it, and did they filter that out?
Yeah, a lot of cell phone camera detectors are actually sensitive to the infrared. Actually, most electronic detectors have sensitivity in the infrared, not the far infrared, but the near infrared. But yeah, more recently, I think they're blocking that. Yeah. And a lot of cameras will block it because there's a lot of reasons for that. Partly is an optical thing. The focus for where the light focuses depends on the wavelength. So in fact, if you set the camera's focus based on the visible light, it will be out of focus for the infrared. So if the camera is sensitive to the infrared, it will actually blur the image. A lot of considerations there, but so that's one of the reasons they block the infrared. Yeah, it's kind of interesting though.
It's recent.
Yeah, it's fairly recent.
Like 2 or 3 years ago, everybody could see it on the phone.
Yeah.
Now they can't.
Yeah, I don't know why that is exactly. Again, I think it's partly this focus. I think the whole camera technology is getting better, so focus means something in a cell phone camera, where I think originally they were pretty limited and they probably didn't really focus at all, and so it didn't really matter that much. But you can actually get, in a higher end camera, like a digital, high-end digital camera, you can actually have those modified to remove the infrared filter and use it as an infrared camera. And there's some that you can buy that are optimized for infrared.
Point
So,
shoots, I think, in the same way.
Yeah.
Apply those to tournament
Yeah, yeah. It's fun. It's a neat, photographically, it's a neat thing to do. But.